You ever plug in your phone and just trust that it's working? I mean, how does the charger know which way to send the juice? It seems so basic, right? But deep inside, there's this tiny, brilliant little traffic cop making sure everything flows in one direction. And today, we're going to figure out exactly how that one-way street for electricity works.
Just let that sink in for a moment. Every single piece of tech you rely on, your charger, your laptop, you name it, has this hidden little gatekeeper inside. Its only job is to make absolutely sure that electricity doesn't decide to go rogue and flow the wrong way. It's one of the most vital components in our modern world, and honestly, most of us have never given it a second thought.
And there it is, the PN Junction Diode. That's our main character for this explainer. We're going to break down what that P and N stand for, see what happens when they join forces, and figure out how they create this incredible one-way effect. So first things first, let's talk about what it's made of.
Now, to build one of these things, you can't just grab any old metal. Nope. You need something special, something that lives in that perfect middle ground between letting electricity flow like a river and stopping it cold like a brick wall. And that's where semiconductors come in.
So what is a semiconductor? Well, the name kind of gives it away, right? It's not a full-on conductor like copper, but it's not a full-on insulator like rubber either. It's semiconductive. Think of materials like silicon or germanium. They're the rock stars of the semiconductor world. They are the perfect building blocks for all kinds of electronics.
Okay, so a pure semiconductor by itself. Kind of boring, electronically speaking. Not very useful. The real magic begins when we start mixing in tiny, calculated amounts of other elements. It's a process called doping. And this is how we cook up our two key ingredients, what we call P-type and N-type materials.
All right, so how do we make these two different types? Well, for P-type, think P for positive, we add impurities that are missing an electron. This creates these little vacancies or holes where an electron should be. Then for N-type, N for negative, we do the exact opposite. We add impurities that have an extra electron just kind of floating around looking for a place to go. So the big takeaway is super simple. P-type has a bunch of positive holes, and N-type has a bunch of negative electrons.
So we've got our two custom materials. Now for the most important part of the story. What happens when you bring a piece of P-type and a piece of N-type material right up against each other? This is where things get really, really cool.
The second they touch, it's like a party. All those extra electrons on the N side see the empty holes on the P side and just rush across to fill them. At the same time, some of the holes drift from the P side over to the N side. But here's the catch. This quick swap leaves behind a layer of stationary, charged atoms right at the border, creating a built-in electric field. It's a barrier that forms all by itself.
And we have a name for this barrier, the depletion region. It's called that because it's been depleted of all its free-moving parts. The electrons and holes have all paired up and canceled each other out right there. So this region now acts like a wall, preventing any more charges from just wandering across. We've officially built our gate.
Okay, so we've built a wall. Now what? How do we actually control it? Well, we can open and close this gate whenever we want, just by applying a little voltage from a battery. This whole process is called biasing, and it's the secret to making our one-way street work.
Check this out. If we connect a battery the right way, positive terminal to the P side, negative to the N side, that's called forward bias. This pushes all the charges toward the barrier, shrinking it down until, poof, it's so thin that current can just zip right on through. But what if we flip the battery? That's reverse bias. Now we're pulling all the charges away from the barrier, making it wider and stronger. And now, no way. Current is totally blocked.
And that's really the whole trick right there. Current flows like a dream in one direction when it's forward biased, but it's stopped dead in its tracks in the other. It's the perfect electronic one-way valve, a one-way street for electricity.
You can actually see this behavior on a graph of voltage versus current. In the forward direction, you see that once you apply just a tiny bit of voltage, the current skyrockets. But look at the reverse direction. The line is almost perfectly flat. Basically, zero current can get through. That is, until you apply a really high reverse voltage, and you hit something called breakdown, where the dam just bursts and current floods through.
So that's all the theory. We've built our one-way street, we know how to open and close the gate, so let's bring it back to where we started. Why does any of this matter? Why is this tiny little component so incredibly important? Because diodes are absolutely everywhere. And most importantly for our story, they are the heart and soul of rectifiers. See, the power coming from your wall is AC. It flows back and forth. Your phone needs DC, flowing in just one direction. A diode is what does that conversion in your charger. It's the traffic cop, letting current go into your phone but never back out.
So this elegant little one-way gate is literally a cornerstone of all modern electronics. Our digital world just flat out wouldn't exist without it. But that leaves us with a really interesting question, doesn't it? Remember that breakdown thing where the diode seems to fail? What if that failure wasn't a bug, but a feature? What if we could design a diode to break down on purpose and actually use that effect for something cool? Well, that's a story for another time.